Okay, so in this lecture, we're going to continue talking about some of the fundamental linear algebra concepts that we use to kind of learn about linear regression with multiple variables. Specifically, we're going to talk about matrices, but also this idea of orthogonal projections. And if you remember back to linear algebra, an orthogonal projection is just where we have two vectors and we try and drop one vector in between them, and that vector forms kind of an orthogonal or 90-degree relationship with one of the vectors. And the main thing to keep in mind in this lecture is that by doing that, what we're really forming is a type of minimization problem where we're getting the vector with the least distance that forms that orthogonal relationship. So that's kind of how the context of it, we'll circle back to linear algebra, not just the fact that we're using matrices and vectors which can hold n dimensions of data, but also that we can use things like orthogonal projections as a form to find the minimization of these vectors and matrices, when they're sort of related to each other. Okay, so remember too that you can also, any questions you have, please post them onto our class discussion board, and we'll get to them as soon as we can. Lots of questions are always good. And we'll start by really quickly going back over spans and projections, and to give you a little more of an in-depth understanding of what's going on when we say that this orthogonal projection is a form of minimization. So you remember back to last lecture, we have two vectors, vector x and vector y, and we have this idea of a scalar w, which scales vector x, and a scalar can be anything that can, it's a number that can change, and it's part of the set of real numbers, but it can change x to either make it smaller or larger or reverse it. So, this would be a type of a scalar of x, and that, and that, and this, and also going the opposite direction, so on and so forth. As long as it lies on x or goes the opposite direction of x, and it scales the vector x. So what we want to find is, given some other vector y, what is the projection of y onto x, and what is the specific vector that we can create, in this case it will be e, that minimizes e. So there, you can imagine some other vector here which forms an orthogonal relationship with x. What is this vector e? And why is this one the minimum, not this one or this one or this one? So that's what the goal is. And you'll probably at some point hear my dog. He's very upset right now because his walk was cut short, so I could come back and do this recording for today. But if you do hear him kind of being upset, my apologies. But okay, so let's go ahead and the claim that we have is there's some vector e, and e orthogonal to x. So it's going to look like that. And we'll say that this is e1. And we have our vector x, and maybe I'll do this in purple. We have some w, and this would be like w1, and this is a scalar that turns x into being this distance. And then we also have perhaps another one, and this is w2x, and this causes, we have another vector here, e2, and we want to know which of these vectors is orthogonal. Is it this one or this one? Who knows? And once you know which one's orthogonal, what is the w that minimizes the vector x to make it, or that the scalar that causes vector x to be at that location where it is orthogonal. So let's say that E1 winds up having an orthogonal projection onto x. Then we know that W1 is a scalar that causes x to be that distant, or that's the distance that we can tell. And so we can use this as a way to kind of minimize this vector. And in order to make that claim, we have to know that the vector e, which is orthogonal to x, is the least distance. Maybe E1 is orthogonal and E2 is not, but how do we know that E2 isn't actually shorter than E1? And so we're going to work on a couple of problems to show that. And quite frankly, we can use, luckily, we can use the Pythagorean theorem to kind of help us out there, since we're just making triangles. So let's go ahead and redraw this. So we had some sort of, and I'll do it kind of like on a 2D surface here. Let's make the drawing easier to see. So we had, this is vector x, and then yellow, this would be vector y, and we wanted to, I'm going to make that smaller actually, so I have some more room to on the other side. Okay, and then we put down a vector here. We said that this was E, and this is orthogonal. And we're going to call this E star because we believe that this vector here is the smallest length of E that we can use. And we also have, we can do this in purple, these scalars here. So we have one which goes to right here, and this would be W star X. And we have another one that goes further than that. I'll do that one in black. We can call this one maybe W prime X. And where that one goes, we can draw another line. And we'll call this one E prime. So the idea here, let's put this in green. So I guess our purpose is to want to show that the vector E star is the shortest possible error vector that we can create. So what we're saying is we have this vector here, E star, and we know that when E star is at 9 degrees orthogonal to X, it's the shortest that E will be. Well, that's intuitively we know that, but we need to show it mathematically because there are, pretty much an infinite number of E's that we can draw and we can project onto X. But in order to minimize E, we know that we can minimize it when it's orthogonal, right? So the second that this shifts over a little bit, that distance becomes longer than this distance. And we can use the Pythagorean theorem to show that. So let's maybe horrible. Okay, so this is the triangle that we're dealing with in question. And we can go ahead and duplicate that triangle over here. So we will have, since we've been using red, let's stick with that. And we know this is a right angle triangle. And we know that we have lengths here. So we have E star and E prime. And if we look down here, we know that we can say that this total distance from the origin, so from the origin all the way to W prime X, is one length. And we know that where W star goes is where we have E star projecting onto X. So where this 9 degree happens is as far as W star goes. So in order to get this length, we can just take W prime and subtract W star from it. So let's go ahead and write that as well. Let's do that one in black. So this is going to be W prime minus, W X. W is just a scalar, so X is the vector minus W star X. And that will give us the length of this side. And this, you can set this up to work whether it's here or whether you just flip this over and we use, let's say, this triangle instead. So this is symmetric. It works either way because we have a right angle triangle. So we want to make use of the Pythagorean theorem to try and see why E star will always be smaller or shorter than E prime, no matter what. So we could pick a single value and do that and show that this works because of the Pythagorean theorem. But in general, this is a little bit of a hand wavy proof. But we want to generalize whatever this value could be, whatever this value could be, to show that as long as it's greater than or equal to 0, that as long as this side is greater than or equal to 0, then this will always be shorter than that. So it's just a quick way to write this using the Pythagorean theorem. If we have, we'll say E prime squared equals vector of E star squared plus the W x, and this is prime, minus the W star x vector squared. So this is let's be the Pythagorean theorem. And we know that this right here, and the way we've set up the problem, is this will be always greater than or equal to 0. And without having to go too much through it, as long as this is greater than or equal to 0, we can put this as vector E prime squared is always greater than or equal to E star squared. So this is a kind of a quick way to show that. So we will say that from this, the vector of E star is the shortest possible error vector. This is the shortest error vector we can find. So why is this important? Well, because we have to minimize something, and if we're not going to be using one parameter, like in the constant model, or the two parameters, slope, intercept, and now we're going to be working in higher dimensional areas, we'll be working with a plane, and we need to minimize that plane. And so we need to be able to do projections like this and understand that this error right here is the shortest one. That's where the goal is, the minimization. So let's go ahead and look at this like with a, let's kind of derive from this a mathematical expression that we can use for W star, because ultimately this E is the result of what we get, this E star, but it's this W star right here that we need so that we can manipulate whatever the vector x is to get that distance. So let's use I guess since we'll try and stick to the color as much as possible. Okay, so the idea here is that the vector E is it's orthogonal to some to some Wx, right? And so like as an equation, this would look we'll use it, that was blue for x, right? Yeah. Okay, so we'll say that Wx times some E vector is equal to 0, right? So this is like what we want right here. And let's go ahead and solve for what W can be. So here we will say we need to take the E vector and replace it. And we know from back here, we want to minimize that. So we can just use the Y vector minus WX vector. So we will say Wx times Y vector minus X vector is equal to 0. Okay, so what do we do? Well, we know we can get rid of this W out here because it's just a constant. So we just divide it out. And, so we can get rid of this guy. And that will leave us with this. And we can use the factorization properties of the dot product, which is what's going on here. to factor out this and make it a more kind of pliable state after we, of course, get rid of this w. So let's do that. So this will give us x bar times x vector times y vector minus be x equals 0. Okay, so that's the first part of the factorization. And the next thing that we can do is looking at this thing right here. Here wx is a vector that's being scaled, and since the dot product is distributive over scalar multiplication, we can pull this w out and rearrange it as w times x vector dot product with itself, and that represents the just scaling of that dot product, which is, I guess, would be technically the squared magnitude of x. So we can rewrite this as now x product with y minus, so we'll pull that w out, then we have x equals 0. Okay, that's looking all good. And after that, it's just some simple manipulation. So we can take the term and rearrange it onto the other side. So this will give us x bar, or x vector dot product with y vector, which equals the scalar times the squared magnitude of x. And then with some simple division, this will give us what we want for w. So this will say w is equal to x times y over the x's. And because this is the best w, since we knew that this was orthogonal to begin with, and that's why we entered that in there, we can call this w star. So what does this mean exactly? Like what's going on here? And what this is doing is it effectively, I'll write it down too, it effectively finds the scalar. So finds the best scalar that projects that y onto x. And these would be like that, by minimizing by the error vector e. Well, I suppose minimizing the magnitude. Yeah, let's put e actually. And so what this essentially does is it aligns well with what the approach to regression that we've been doing, and that's kind of where we're working with this towards with this. So this is a good thing to keep in mind. Oops. Okay, so we're kind of building towards this idea of working with multiple in multiple dimensions. But just to make this clear, we kind of talked about the idea of minimizing the e vector. What we're doing is trying to find what vector that spans the x vector is closest to the y vector. And from the last few slides, we found that the answer is this. This is w star is the x vector dot product with the y vector over the x vector dot product with itself. And that gives us the e vector, which is this idea of a minimization problem that we're working with. And one thing to think about, and I'll be probably repeating this now for a third or fourth time, but it's important to comprehend, is we have an x vector right here, and then we have some y vector here, and we want to know what w, in black, can we use to find the minimum possible vector of E, which is orthogonal, and that's our E star. And we want specifically the minimum possible length of E. And E, of course, it does that when we get that when E is orthogonal to X. So this W is how we're scaling the span of X. But what we really want to think about is, when we go to more than one X. All right, yeah. So let's go ahead and think about that now. This x1, x2 here is not it's not x to the first power or x to the second power. This just denotes the vector x1 and the vector x2. This is important because you see this plane here. We have x1 and x2. And this is a video made by Jack Dieterman, who was a tutor in a previous DSC40A class. Who made this kind of three blue, one brown-esque video using the same library, Manum, that Grant uses in 3 blue, 1 brown to make those videos. And what Jack was trying to accomplish in this video, and you can go ahead and click on the animation and watch it at any point during this lecture, but now would be a good time to do it. And when you're watching his lecture, I think it's like a minute or 2 long video, what you'll see is that we have, instead of just one X, like we had here, we have 2 X's now, and the span of 2 X's is this entire plane, right? So with this here, we can show that that these 2 X's, this is their entire span. They can reach any point on this plane. And in his video, he was trying to show that given this span, we can find wherever the y vector winds up being orthogonal to this plane, we can find the best E for that. And we do that by finding the W that best minimizes it. So what we'll kind of do in the next two or the next few slides is we'll try and find out how do we solve for or find these W's, because if we can do that, then we can find how we minimize. We kind of do the same minimization problem, but instead along one X, we do it along a span. And that's important because the span is kind of the first time that we're going to 3-dimensional space to doing this. And in linear regression, you typically do it in more than 3 dimensions. And as you get into higher dimensions, we're dealing with instead of a 2D plane, we're dealing with hyperplanes. And we want to have this kind of geometric and algebraic ideas of how to work with vectors and projections and spans and what that means. So this video is a good way to kind of get some of that intuition behind it. And once you've done that, we'll go ahead and look at minimizing projection error in now multiple dimensions instead of just one. So now that we're going into multiple dimensions, before we had just one vector, x, and now we have multiple vectors, x1 and x2, which are both in the span. And what we want to find is what vector in this span is as close to y as possible. And so what that really means is, what vector is going to be orthogonal. So for the span, where x1 and x2 are vectors in that span, we can write that as follows, w1 x1 plus w2 x2. And we want to know kind of what are the w1 and w2, so the 2 scalars, when dot product with our error vector equals 0, because when the dot product is 0, of course, we have 2 vectors that are orthogonal to each other. And if we find that, then we know that vector winds up being the vector that's most close to y in this case. So the problem is when we have an equation that's kind of written like this, it's extremely difficult to solve. And so what we want to do is we want to find a way to try and rewrite this into like a system of equations. And we'll kind of show you how to do that in the next slide. And of course, that's also not going to be the best way for us to solve this. Once we get into higher dimensions, we have many more x's than just 1 and 2. So that will be where we go into bringing matrices on board. But how do we kind of rewrite this? We'll start with that into a system of equations. And in order to do that, we have to kind of think about what is this equation saying. We can decompose this large equation into 2 smaller problems. One for both x1 and one for x2. we can do that by making an assumption, and that assumption is that both x1 and x2 are both individually orthogonal to the vector e that we're trying to find. And the reason why we can say that is because if both x1 and x2 are in the span, then we know that they are linear combinations of each other. And so if e is orthogonal to x1, it also must be orthogonal to x2. So how can we think about this and how can we rewrite it? Well, let's try it out. So let's rewrite this part right here, and this will just be w1 x1 plus w2 x2 times e, and of course we get that e from right here, right? That's this entire thing, but we don't really care about that thing right now. So what we're trying to show is that this vector e, which is our error essentially, we want to show that if you're orthogonal to either one of these, then you're orthogonal to the sum of both of these, or all of your x's, because of that idea that they are a linear combination. So we can use the properties of the distributive properties to rewrite kind of this part right here. I suppose I should add that there. So what would that look like? Well, we can distribute the e into it, and this will give us, let's see, w1 x1 e, and then plus w2 x2. Whoops, I'll write that a little bit better. All right, and we can further simplify this by pulling out the w's. So this will be w okay. Now then, we have something that's kind of familiar to us. We have x1 times e and x2 times e, and we know that x1 times e and x2 times e both should equal 0 if they're orthogonal. We see that right here. So we can actually just reduce those to being 0. So this would just be w1 times 0 plus w2 times 0, which of course is just 0. So what's this essentially saying, what we've kind of shown here, is that even though we have this kind of large multifaceted dot product equation going on here, we don't actually have to solve this at once. We can decompose this into two separate things because these are a linear combination. So we can just say that our error vector times one of these is orthogonal, implies that the error vector times the other one would also be orthogonal. So this gives us a nice way of being able to rewrite our equation into something that's much simpler to work with. And remember, when we have this type of equation, what we're really trying to do is to solve for the scalars, the w1 and the w2, because that tells us how, because x1 and x2 both together span the entire plane, there are an infinite number of w1s and w2s we could pick, but we're trying to find the w1 and the w2 that make our error vector orthogonal to our x1 and x2. So really that's what we're trying to find. And we all kind of make that explicit here. And in keeping with the tradition that we've been doing, that's the w1 star and the w2 star that solves this the system of equations here. The problem, though, is that for any system of equations, and as all of you have probably done in the past in high school or whatnot, solving these things when you get into more variables becomes quite literally a pain in the ass. So typically, we're not just dealing with x1, x2, but we're dealing with maybe x100 or x200 or x50. And so these things become really, really difficult to do. So for that, we really want to be able to step up our game a little bit. And in order to do that, we really want to begin to use matrices, because once we can write the system of equations into the form of a matrix, there's a lot more powerful ideas from linear algebra that we can use to solve these equations and find out what the optimal vector is. And this is what we're going to be working on next. But before, of course, we can do that, we should take a little side quest and review some fundamental matrix operations and matrices ideas that we can use from linear algebra, and some of the key things that you should remember from linear algebra or Math 18. So we'll go ahead and do that next. Okay, let's do a pretty rapid overview of matrices, just to make sure we're on the same page in case it's been quite a while since you've taken 18 or linear algebra. Matrix is a n by d table of numbers where we have n rows and d columns. And so in this case, this table would be a 2 by 3 matrix, right? Because we've got 2 rows and 3 columns. And rows always comes first and then columns whenever we're naming matrices. And the way we're going to describe matrices in this class, which is pretty typical, I'd say, is vectors are with lowercase letters and then matrices are with uppercase letters. So when we have something like, you might have seen this term before, we say that the matrix A, which is a 2 by 3 matrix, is in the set of matrices with 2 rows and 3 columns. So is in the set of matrices with 2 rows and 3 columns. And that's just how we're going to, or that's just the formal definition, I suppose you could say. But the intuitive way to think about it is that a matrix is just a stack of column vectors that have been kind of concatenated together. So matrix A is really just 3 matrices, or sorry, three column vectors, which are 2 and -1 and 5 and 5 and 8 and -3. So that's the main idea. The main way to think about matrices. Some of the simple operations that we can do is we can, of course, add matrices together. We can only add matrices if they have the same exact size. So both of these matrices are 2 by 3, and this 2, 5, 8 is the same one from A. And the other page, we'll be using that throughout the next couple examples. This is also a 2 by 3. And so what we do is we do what's called an element-wise operation, where we take this value and add to that one, and take this one and add to that one. So maybe just to highlight a little bit, we have 2 and 1 and 3, and then we have 5 and 2 and 7, so on and so forth. Okay, now with scalar multiplication, we take just a value, a scalar, and we multiply it, of course, element-wise as well. So if we take 2 and we multiply it by 2, that gives us 4, and we just kind of do that across the entire matrix in an element-wise fashion. All right. And again, it's important to remember that it is element-wise. And some of these operations, like addition of matrices or scalar multiplication, or in this case, matrix-matrix multiplication, it winds up being very good to have an intuitive sense for these things, because when you start kind of writing machine learning code and you really get into the kind of gritty nature of machine learning, or perhaps you're writing some stuff from scratch, you're going to wind up doing a lot of matrix multiplication and matrix kind of operations, especially when you start working with the NumPy library. It's all matrices. And so having an intuitive idea of what's going on with matrices and when you're multiplying them, how that works, it winds up being very helpful and making it kind of much more fluid way to work. So one of the most important things, and probably one of I think, this is pretty simple stuff, but this is also simple once you wrap your head around it, but it can be a little tricky. It was probably a little tricky the first time maybe you learned it in linear algebra. But the idea of how matrix-matrix multiplication works, in your data science careers and data science classes, you're not going to be asked to do a lot of this by hand, but you are going to be doing quite a bit of it through computer operations. And so understanding those matrix-matrix multiplication ideas can be quite helpful. So the idea here is that if we want to multiply 2 matrices, A and B, the only way we can do it is if the number of columns in A is equivalent to the number of rows in B. And one simple way to think about it is that if you have A and you have B, and I guess I'll use the same colors. If you have an N by D and then a D by P matrix, these two inner dimensions need to match. right? So that's the important thing, is this interdimensions. So how do we actually do this? And typically, or a very common operation is this idea of a transpose. So that's where we take a matrix and we kind of pivot it or rotate it so that well, I guess one way to think about it is your rows here wind up becoming your columns, and in the same order. So your first row becomes your first column. So if we wanted to take the matrix A and multiply it by itself, we would transpose it, because of course we can't multiply. You know, A is a 2 by 3, and you can't do a 2 by 3 times a 2 by 3, right? Like, these two things don't match. So we have to transpose one of them so that we get a 3 by 2 multiplied by 2 by 3. So let's go ahead and rewrite A as a transpose. So we say that A transpose, and it's not A to the T power, it's just A transpose, is going to be so we take the first row, 2, 5, 8, that becomes our first column. 2, 5, 8, and -1, 5, -3. So I guess one way to kind of think about it also is you take the diagonal this way, and you just kind of like rotate it, like flip it around, like spinning it on its axis from a horizontal to a vertical thing, and that kind of does the same thing. So another way to think about it. But this is now a 3. This is now a 3 by 2, and remember this is a 2 by 3. And since the two here, the inner diameters match, we can do A transpose times A. So let's go ahead and figure out what that would look like. And the way to think about it is this is going to be a operation where we kind of take the column or the rows in A transpose T, so that's 2, -1, 5 and 5, 8, -3, and we're going to take all three of these and dot product them by the first row, individually. Then we'll take each of these rows again and dot product each one by the 5, 5, and then again by the 8 and -3. And so what we're going to wind up getting is a matrix that is 3 by 3, just the outside dimensions. So 3, 3, 3, 3. Okay, and let's solve a couple of these. So we would first have let's make like a little scratch area here. The first one would be 2, -1, dot product with 2, -1. 2, -1. And what that's going to equal is we're going to have 4 plus 1, which equals 5. So that gives us 5. And we'll do the same where we have 2, -1 with 5 and 5. And that's going to give us 5 again. So this will be 5. And then we'll do the last one. Again, we've already done this one, then we did this one, and now we'll do 8 and -3 multiplied by this. So that's going to be 8, -3 with 2. Actually, I made a small, it winds up being the same thing, but small error in the last one. I know, that's correct. Well, kind of 5 and 5 with 2 and -1. So 8 and -3 with 2 and -1. And this winds up being 8 times 2 is 16 plus 3, which equals 19. So this gives us 19. And just to make it clear, we had this and this gave us this, and we had this. I guess I can kind of erase this one. Maybe this one isn't the best, but this and this goes here. And now let's draw it this way. They're all using, it's terrible. They're all using that column. So what would be, I guess we just do it this way. What would be the very last value here, right? So we'll have something here, we'll have something here, 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 and here. But what's this very last one? Just so that we're all on the same page, this very last one would be 8 and -3, because we're going to go through all the columns again for A transpose. So 8 and -3 by, you guessed it, 8 and -3, which goes 64, plus 9, 73. So this would be 73, and that's just going to be that and this one. Okay, so that's a very quick overview for some of these key concepts, beginner concepts, but things that you should just remember. Let's go ahead and try and pause the video and think about this question. Assume A, B, and C are all matrices. Select the incorrect statement below for all of these, and think especially hard in a generalized manner the types of operations that you can do with matrices that we've just kind of thought about. That is scalar multiplication, matrix and matrix multiplication, and then matrix addition, and what properties of those operations must be true in order for them to be valid operations. Okay, so the correct answer for this one will be C, or I suppose C is incorrect, the incorrect statement, but C is the correct answer to this question. And why is that? Well, we can create an example. So let's say that A is some matrix, which is a 5 by 7. And B is some matrix that's 7 by 5. And that would result in a 5 by 5 matrix, right? Because we have the outer dimensions, and we can also construct the same thing where we have B times A. This would be a 7 by 5 and a 5 by 7. This would give us a 7 by 7, which would not, of course, be the same thing. So in the general sense, this would be an incorrect statement, C. Okay, so just to make it explicit, different dimensions. Okay, so let's go ahead and talk about this idea of matrix vector multiplication. And so what we mean by that is we have right here V, which is a column vector, and we want to begin to think about different ways to understand matrix vector multiplication. So in this case, V is this vector, and it's an n rows by one column, so we call this a column vector. And we suppose that we have some matrix A, which is in the space of matrices that span n by d in size. And we want to think about, in order to multiply this vector and this matrix, what has to be valid. So if we want to do A times the matrix, the column vector V, what must be true? And we can write this down as, let's see, we have A, and this is going to be, as we know from right here, n by d. And we have some vector, and this vector has to be in d by 1 dimensions because the inner dimensions must match. So what this is going to give us is going to give us some vector that's in, this is going to be, or this will give us some vector in this, with d components in it. And I'll just write that down. So D components, and this is what we would get. Now, if we wanted to take V, which is a column vector, and multiply it into A, we would need, of course, transpose it, which would now give us a row vector. And what would that look like? So this would be V transpose, which is a 1 by n, and we're multiplying it with A, which is an n by d. So that's going to give us a vector. It's in the elements with n components. So this has n components to it. Okay, so why is this important? Well, this is important because when we think about what a matrix is, like A, and what a vector is, V, we want to know how we can actually multiply these together and what components we're going to get from it. I suppose one good way to think about it is your vector V is like a set of weights. And we want to multiply these weights into a matrix. So this idea of what type of either column vector or row vector we're going to need, what those dimensions are going to wind up being, is an important idea. Now, why that's important is because there's two predominant ways to think about this matrix vector multiplication. So one of them is this idea of a dot product, and the other way that we're going to look at it is an idea of linear combinations. So the dot product way of thinking about matrix vector multiplication is the way that's kind of typically taught in linear algebra, and that's what we were doing before here, when we were just kind of taking two matrices and then we were taking the dot product between the inner rows and columns as we were multiplying it. Here we're kind of doing the same thing, except instead of two matrices, we have just a vector, which a vector really is a one-dimensional matrix, either in the column or row space. So what does this actually look like? So if we have A here, I'll do this with orange. So A, this is a 2 by 3. This is the same A we've been looking at all along. And we know that the vector V is a 3 rows by 1 column. Then we want to, or maybe it would be better to, just in yellow still. So we say that the vector V is in the space of 3 dimensions. And when we take A and multiply it, let's say by V, what are we going to get? So let's go ahead and do that operation real quick. Let's stick to our, we'll go with purple. Okay, so A times V is going to give us some matrix or some vector. And we know that A, I'm supposed to do it here, A is a 2 by 3 and V is a 3 by 1. So we just look at the, make it a little better. We just look at the exterior dimensions by 3, 3 by 1, and which is going to be 1 and 2, and thus we know this will be a 2 by 1, 2 rows, 1 column. So let's go ahead and actually do the calculations because why not? And maybe we'll do those calculations over here. So we can just move this here. So for the first one, we're going to have just, we're going to have 2, 5, and 8, and that's going to multiply 2, -1, and -5. So that's going to be the first. So the first one is going to be 2 times 2 plus -1 times 5 plus -5 times 8. And the second one that we're going to get is going to be negative this bottom row here times this vector, column vector, which is going to be 2 times -1 plus -1 times 5 plus -5 times -3. So this is going to be 4 minus 5 minus 40. This is going to equal -41. And then this one's going to be -2 -5 plus 15, which is going to be 8. Okay, so what we're going to wind up writing is -41 and 8, and that's going to be our that'll be our new 2x1 vector that we got from this matrix vector multiplication. And we go ahead and use yellow just to make it clear. Okay, so that's essentially the operation, and from that, we'll go back to our yellow, this gives us a 2. So we've kind of essentially, by doing this matrix vector multiplication, we've reduced the dimensionality of this data. In some sense, we've gone from, I guess that this is a little bit missing too. But the key idea here is just this idea of this dot product operation. So just to show you kind of what's going on. This is pretty familiar, but this is just a dot product approach, kind of like plug and chugging approach to solving this. Now, what's the other way that we can think about this? That's the idea of matrix vector multiplication in the sense of using, we're thinking about the operation as a linear combination of your columns in A with some column vector, which in this case, we would think of them as weights, because that's the traditional thing in machine learning. And this is something that we kind of saw back here when we first thought about a matrix as just a concatenation of a bunch of column vectors that are just, smushed together. So if we think about it that way, then here we have 2, 1, 2, -1, and we have, we'll try a, maybe just to make it easier to see, I'll do a different color. We have 5, 5, and then we have 8 and -8 and -3. And just move this, actually give us a little more room, because I'll wind up just doing the operations in here. Okay, so those are the 3 column vectors that are kind of smushed together. And then we have these values over here, 2, -1, which come from the column vector V, -5. Suppose I should have just done this from the beginning. Okay, so, and then we're going to add these. And it's not going to, of course, we still get the same answer, which is, what was it, -41 and 8? Yeah. So that's still, it's all fine. Nothing here has changed. But the important thing to note, this is AV, is this is just a linear combination. Kind of like from the very beginning of this lecture, where we were really kind of thinking about these things in terms of those x vectors with weights, so and in multiple dimensions. So we had those as W1 x1 plus W2 x2 plus maybe W3 x3, and these are kind of like this idea here. So we're kind of seeing the similarity of having vectors in higher dimensional spaces, and then using matrices as a way to think about these operations. And in particular terms, we have this column vector V, which is acting like the scalar weights when multiplied to this matrix A. So, and remember, x1, x2, x3, these are just vectors with, it doesn't matter the size. They could be 2 by 1, 100 by 1, 10 by 1, it doesn't matter. It's all linear combination, and these W's are just scalars, and we can store those scalars in its own vector. and multiply them across. Because of course, when we describe this equation, this idea or concept like this earlier in this lecture, we kind of had set up as a system of equations or just one really nasty equation. But now we have a way of holding these weights in its own vector and then holding these vectors together as a linear combination in some matrix, and we can multiply this out because we have those operations. We can do that with the dot product, but we have a way of dealing with these two things now, the weights and the vectors. And so this is a particular nice way to package this information. And when we start working with, or when you start working with more kind of like heavy duty machine learning, this is especially true in like neural networks and deep learning, where you have just like extremely large matrices and you're doing many matrix multiplication problems, hundreds of thousands of them at once when you're training these machine learning models or doing inference. These essential operations of matrix vector multiplication are what's making that kind of stuff possible. So understanding this connection and how we're going towards using matrices now to do these operations in higher dimensions, it's an important concept to kind of wrap your head around and make sure you understand. This is going to help us when we start to go towards linear regression and kind of put this back into the realm of linear regression. So hopefully this is a good review, not just a good review, but also kind of setting the stage for how to think about this stuff in slightly different terms than what you may have been taught in 18 or linear algebra, which might have been more of like a plug and chug approach to learning this stuff. But this is kind of more of a intuition idea that we can then use linear algebra and apply it to machine learning. So this is where we're going with this stuff. We'll go forward and kind of, now we've done some fundamental matrix stuff. Let's go back to spans and projections and bring this back to linear regression. Okay, and just finally, a way to kind of formally articulate, write this idea of a linear combination of columns of A using the weights in the vector V is to have it look like this. And this idea here is what we're going to use going forward in the rest of this class to kind of solve a fundamental question we were asking towards the beginning for trying to solve that more complex system of equations. Okay, so now we're kind of in this area of multiple dimensions, and we want to begin to solve that system of equations. So we're now back to our traditional x1 and x2, and we want to make sure that we're able to bridge the gap between the stuff that we talked about earlier in class and the stuff that we had just finished talking about. So, the idea here is what vector in the span of x1 and x2 vectors is closest to y. And remember that in order to figure that out, we have to learn what those w's are. So this would be w1 x1 plus w2 x2. And the answer to that, to what those w's are, is, and this is probably best to write blue, 4x1 and 4x2 we're going to kind of dot product that with E, our error, which is this whole thing here, and those need to be equal to 0 so that they are orthogonal. So our error vector. So that's what we're trying to determine. And the way we're thinking of that now is to create a linear combination of these x's. So we can say that we have w1 x1 plus w2 x2. And so what this w vector winds up being is just a column vector for the weights. And we can kind of package these x1 and x2 and we put them into a single matrix. So this is nothing new, exactly what we've seen. This would be 2, 5, 3, -1, 0, 4. And just to make it extremely obvious what's happening, Okay, so we're now expressing this span of x1 and x2 as just a single matrix X. And what that gives us is we say that X times our weight vector is equal to W1, a little bit better, times 2, 5, and 3 plus W2 times the vector -1, 0, and 4. And the way we're expressing it here originally is exactly the same way we're expressing it now. So these are essentially equivalent. We can say that this is equal. That's this packaging idea that we're thinking about now, where we're expressing our x1 and x2 vectors into this very nice and neat matrix of X. And then we're going to pull out those W's and turn them into a separate vector as well. Again, this is the same thing we've been talking about. We're just kind of trying to take the original idea that we had of the system of equations and this new idea of a system of or a linear combination with the column vector times the matrix and kind of pulling them together. So that's X now. Our Y hasn't changed. That's still the same. But what we can do now is when we're trying to solve this equation, which is what we're going to spend the rest of this lecture doing, we can express this now more clearly with just this X. And remember that the X here is really just our weights with our vectors for X. So our individual scalars with our individual vectors are now being expressed with this nice little matrix X. And then, of course, we still have the W there as well. So I suppose it would be better for me to do that. Okay. So this is what we're going to now work on trying to solve. Okay, so in order to simplify our problem, that is to take this nasty looking thing and simplify it, we're going to do two steps. Well, primarily two ideas. The first is going to be the idea of this linear combination. And so we're going to write down, well, really what we're going to be doing is reconstituting these weights and also these X vectors in terms of a matrix and a weight vector column. So let's go ahead and take our, let's do it here. We have our W1, X1 plus W2, X2. So now we're saying that this thing is essentially equivalent to the matrix X times the vector W, right? And we have this idea of some weights. We don't know yet. We're trying to solve for those, but that's kind of what we're going to have. And we're saying that these things are functionally going to be packaged into this X times the weight vector. So we can also go a step further and say that E right here, so the vector E is equal to the vector Y, nothing different there, but we can re-express all the stuff in here now and here into one simplified thing. So let's go ahead and do that. So we had Y vector minus W1, X1 minus W2, X2. And now we're just saying that this is essentially the vector Y minus X, the matrix X, times the weight vector. And this is a very nice thing. And now when we go ahead and sort of apply that change to all these, we'll have X1 with vector Y minus X, the weight vector equals 0, and we'll have the same thing for the second vector of X, which will be Y vector minus x times the weight vector equals 0. Okay, so how we got to this simplified version of this is through the idea of linear combinations. And that was from right here. Your matrix vector products creates a linear combination of the columns. Now the next step that we're going to take is going to ask us to consider the idea of using the dot product. So that was back over here, this matrix view of taking the dot product for vector v times some matrix. So this is how we're going to actually further simplify our equation. So let's go ahead and rewrite this. So this will be x1 minus xw equals 0. And again, we're just rewriting these. That will be x2. I can do that a little better. Okay, and remember that is equal to E. Just remember that. Okay, so what are we doing? Well, we have x, and if we go back, x is 253, negative 104. So let's write that down. We have x, which equals 253, negative 104. Okay, so this is a 3x2 matrix, and we're saying this is essentially equivalent to our individual x1 vector and our x2 vector, right? So these things are equivalent. We're just taking these individual x vectors, and then we're concatenating or kind of stacking together the individual column vectors. And we know that we have to do some sort of multiplication here with vectors. So in order to do that, we need to take the transpose of x, because we want to multiply that by some weight vector. And that weight vector is going to be in the same dimensional space. In order to multiply that by x, as we've seen in previous slides, we need to take the transpose. So what would that look like? Well, if we transpose this, remember we just draw a diagonal from left to right, and we just kind of flip it around. And so xt gives us, should be 2, 5, 3, and negative 1, 0, 4. This is now our 2x3 matrix. And we're going to multiply that by, in this case, it will be it's this vector right here. So we can say, I mean, it really doesn't matter what the numbers are. But we'll say just yellow, whatever, 3 ones. So this, of course, being a 3x1 vector. So this winds up, whatever that vector winds up being, we can now multiply this matrix by some column vector. So the rows of our transpose matrix are the columns of x. And we can see that these rows are these columns. Nothing new there. But now what this does, this idea here, is it allows us to reframe these equations into one single equation. I know we're kind of going from one equation to a system of equations back to one equation, but the idea now is that we have an equation that's written in terms of matrices and column vectors, which is very nice. So this goes to x transpose times some vector y minus matrix X times our weight vector, and that's going to be 0. So what does this look like now? Well, remember this is our error vector that we're trying to determine how to make this orthogonal to our x's. So this is going to further go down into x transpose with our e, and then that's going to equal some, do this like this. Okay, remember this is x transpose times our e vector, and that's going to wind up equaling our x vector 1 transpose e, x2 transpose e. Maybe I can write that a little bit larger. It's getting kind of messy. X and x, and this will be 1 t 2 transpose vector e. That's going to be equal 0. And I suppose this is a up here the same thing too. This would just be a vector of zeros. And let's highlight these things. So we have essentially taken, I suppose you could say, this thing over here, and it's kind of turned into this. And that's a similar thing for this guy. Okay, so this is a nice, simpler, compact way to represent that same equation, and we can now work with this, which is what we will continue to do. And one other actually really quick important thing to make very clear here, I didn't really highlight it, but this right here is our simplified equation that we care about. This is just going through this process right here. This and this is just a way to show the equivalence between this and this. But here we're taking all of our basically all of our e vectors and dot producting it into the transpose version of x, which is what this is doing here. Exactly. This is just a more compact way of writing it, and writing it in terms of a matrix, because we're taking our x1 and our x2, and we're saying this is x, but now x transposed, which allows us to say remember the rows of x transpose are the columns of x, and since x1 and x2 are the columns of x, we just transpose it, and then we can combine all this stuff, and that's how that works out. So this is the key idea here. Okay, so yeah, the whole point of what we've been doing is to try and find this weight column vector w star, and that's the vector that's going to get us, that's going to allow us to scale our x's such that we find the vector which is closest to y. Now this right here is what we had on the previous slide, right? X transpose times y minus x w star, and this is, I'll just yeah, we'll highlight it. Why not? So this is the key idea that we've been building up to, is how do we sort of get to this? And that's what we've done. And this is what we saw on the previous slide. So this was the last few slides. Now, we want to actually be able to solve for w, to get that w star. So there's some simple things that we can do. This is kind of leading to this idea of something called the normal equations, but we can expand this out, and that gets us x transpose times y vector minus x transpose times x times w vector equals 0. Of course, we can also add this term, and then now we've got this thing. And eventually what we want to do is to take our, we want to get the w vector by itself. So we'll have to get rid of this somehow, which means probably multiplying it by its inverse and putting that on this side, which will get w star or w vector by itself. But this is, these kind of calculations begin to go into the realm of what we want to be able to plug into a computer to do, because they get quite enormous. The idea here is this term, this equation, is what's known as the normal equations with a plural s. Maybe I'll put that here. Why? Well, because why not? People like to name things many different ways, and much like we can name columns in a data set as features or variables or attributes, normal is just another way of saying orthogonal. And equations, well, yes, even though this is one equation, it represents, really, from what we've seen, is one, but it represents a system of linear equations. And we've seen that from this concept right here, right? We had this system of linear equations, and we were able to simplify it into one equation, and then that's what we have here. When we start to begin to solve for w star, we get to this step. This is kind of what's known as the normal equations. Now, of course, we'll want to simplify w squared, which we can do. And when we have that, what we're really trying to do is find those w vectors, the w vector, and specifically, if you are to, let's say, plug these numbers in for our example data sets that we've been using, you would get just a vector, and that would be the scalars that we would need to apply to each of our x vectors to get it as closest to y as possible. So the whole point of this lecture, which is now starting to go on a little bit long, the entire idea here was to figure out what these numbers are. So determine not just what, but how we come to calculate these values. So that was the whole point. And a special consideration is to really make sure you understand why the weight vector, the weight column vector, equals this, and how we got there, which of course is by taking this equation, which we got from here, and further simplifying it and solving for the w star. So this has gone on long enough, so we'll go ahead and end it here, and we'll begin to use these ideas now to do linear regression in multiple dimensions. So that's what we'll cover in next lecture. And maybe one last quick thing to remember is, not only do we try and find out what these numbers are and how to calculate them, but the goal was to solve an optimization problem, and that's really what we've done. So if you, I guess really quickly, I'll just think back to, we had this y vector, and then we had some x vector, where that's orthogonal, and trying to find what this w is. That is a minimization problem because we are finding the optimal value for the scalar w such that we determine when the vector e is orthogonal. And that's the whole point of this. And when we can do this in multiple dimensions, and instead of a single w, we have a vector w, right? Because we have multiple x's, then now we're cooking, because we're going to have the ability to do this in high dimensions, which is how we're going to solve linear algebra or linear regression problems and optimize to find those weights. Okay, so that's the last thing I want to talk about. We'll see you next lecture.